We're talking about combining functions. So just like we can combine numbers, we can also combine functions. So we have 4 ways to do that. We can do sum, difference, product, and quotient. So these are a few different ways to write the same thing. First, we're adding 2 functions together, then we're subtracting 2 functions, then we're multiplying 2 functions, and then we're dividing 2 functions. For the combinations of functions, the domain is the set of all inputs x belonging to both the domain of the function f and the domain of the function g. For quotients, the domain also excludes all inputs, which cause g of x, which is the denominator, to equal 0. So we're going to take a look at what this all looks like in action. We got 2 functions, f of x equals 3x plus 1, and g of x equals x minus 1. The instructions ask us to find the domains of f plus g, f minus g, f times g, f divided by g, and also compute what these functions will actually look like once we do the arithmetic as well. So when I look at f of x and g of x, they're both linear functions, so I know that the domains on both functions will have no restrictions. My domains for both f of x and g of x will be negative infinity to positive infinity. So now I'm going to find the function f plus g of x, which I know is just f of x plus g of x. So all I'm going to do is I'm going to write the first function, 3 of x plus 1, and add x minus 1 at the end. Then I'm going to simplify. And my domain for this function is where the domain of f of x and the domain of g of x overlap. But since they're both all real numbers from negative infinity to infinity, my domain for this function is also negative infinity to infinity. We'll do the same thing with f minus g of x. That's f of x minus g of x. And we have 3x plus 1. And I'm going to subtract the whole quantity g of x, which is the quantity x minus 1. So I have to do a little bit of distributing with that negative, but I just know how to finish out that simplification. And I end up with 2x plus 2 is my new function. The domain is the same thing, where the domain of f of x and g of x overlap, which we know is negative infinity to positive infinity. Now we're moving on to multiplication. F of x times g of x. And what's going to happen is I have 2 linear functions. When I multiply them, I have to FOIL them and I'll get a quadratic. So 3x plus 1 times x minus 1. We'll go through and multiply that out. 3x squared minus 3x plus x minus 1. I'm going to have 3x squared minus 2x minus 1. And I have the same thing with the domains as I did before. My domain will be negative infinity to positive infinity. And this is where it gets a little bit different when I'm dividing. So I'm still just going to set up f of x over g of x. We have 3x plus 1 over x minus 1. There's nothing to cancel out here, but there could be if you had different functions. And so now our domain of both functions is still negative infinity to infinity, but we have this restriction because this is a quotient, this is division. So that denominator, g of x, cannot equal 0. So I need to find the x value that makes g of x equal 0. So what's going to happen is I'm going to set x minus 1, which is g of x, equal to 0, and figure out what that x value cannot be. When we solve that, we get that x cannot equal 1. So my new domain will not include 1. So it will be negative infinity to 1, union 1 to infinity. Another way to combine functions is called composition of functions, and we can think of this like substitution that you learned previously in your other math classes. So our notation for a composition of functions is written f of g of x. You can write it like this, or you can write it with this circle in the middle, still f of g of x. It is not f times g, and it is not fog, it is f of g. So think back to substitution. Normally we usually see f of x as our function, but instead of x, we have g of x inside of our function. So we're going to substitute g of x for what that function actually represents, which is 3x plus 1. So you can see I'm writing f of g of x is the same as f of 3x plus 1. So now 3x plus 1 is my input to the function f instead of x. So wherever I see x in f of x, I'm going to replace it, substitute it with 3x plus 1. So instead of x squared, I'm going to have 3x plus 1, the whole thing squared as my new function. Now all that's left to do is simplify. So again, I have something that I need to FOIL. So a formal definition of the composition of functions is given two functions f and g. The composition of f and g is the function defined by f of g of x, and we have another notation. The domain of f of g consists of those inputs x in the domain of g for which g of x is in the domain of f. So it's a little bit hard to wrap your head around, so let's do an example to really see what that looks like. So just looking at the domain of f of x by itself, I know it's a rational function, and my denominator, which is just x, cannot equal 0. So my domain is from negative infinity to 0, exclusive, union 0 to infinity. Now g of x is a linear function, so there are no restrictions on the domain of g of x. So according to our definition, we're looking for inputs for g which provide g of x's that fit our domain of f of x. So we know that our domain of f of x does not include 0, which means that a g of x cannot equal 0. So then I need to find out what values of x make g of x equal 0, so I know not to include them in my domain of f of g of x. So I'm taking my g of x, which is x minus 3, and figuring out what value of x makes that 0, which is at x equals 3. So we know our domain of f of g of x cannot include 3. So we're going to go from negative infinity to 3, union 3 to infinity. And if I just want to prove that out a little bit, I'm going to go back to my f of g of x function, which is 1 over x minus 3, and I'm just going to find a domain by looking at that function. And I know that x minus 3 is the denominator of that function. That denominator cannot equal 0. 3 is the x value that makes that equal 0. So this checks out with my domain. Now we're going to explore the compositions f of g versus g of x. Are they the same or are they different? So I'm using the same f of x, g of x, and f of g of x that we just looked at in our last problem. And I'm going to go ahead and find g of f of x this time. So I'm going to start with taking f of x and inserting it, substituting it into my g of x function, which was x minus 3. So now I have f of x minus 3. When I plug in f of x, I get 1 over x minus 3. So these are two totally different equations. 1 divided by x minus 3 is different from 1 divided by x minus 3. And we'll just check our domain on this one really quickly. So the only thing I see with it that's a restriction is that the denominator x cannot equal 0. So our domain is negative infinity to 0, union 0 to infinity. And this is a different domain than our f of g of x function, which we found earlier. All right, we're almost done. We're just going to go over evaluating compositions of functions when I give you an x value to put in. So there's two ways to evaluate this. One is to find f of g of x, the function, first, like we've just been doing, and then at the end plug in 2 into that function for x. Or we can work inside out with what I'll call the substitution method. So first, I'm going to find g of x at the point x equals 2. So it would be g of 2, we get negative 1. I'm going to plug that negative 1 in to the f function input. So when I plug that in, and I'll end up with the same value that I did on the left.